Okay. So what we were doing last time was input and output queued switches, and I actually have given the example. And why we were doing input output queued switches? Because we were looking at a crossbar and how to implement a packet switching system using a crossbar. That was basically is the idea. And what I had actually mentioned that there will be inputs and there will be correspondingly the outputs. I am showing it on left and right. Crossbar we always show from left and bottom, that does not matter actually. Okay. I am just for the sake of showing, I am showing it. And what we had was that all the packets will be coming in synchronized slots. So at the beginning of the slot you will set the crossbar, depending on whatever cross connection you require, the packet will move through. Then the next slot will come, again you will do the same thing, and so on. You will keep on doing it every time the packets will be switched out to the appropriate outgoing ports. Sometimes it will be possible that two packets will be there which want to go to the same output. That is a contention, output contention. One of the packet has to be dropped if it is only a crossbar, because technically the speed at which the packet is or bits are going on this line, packets going inside the crossbar and packets which are bits which are going on the outgoing lines, they are all three same. So speed of factor is 1 in that case. So one of the packet has to be either dropped or it has to be buffered if you can keep memory here. If you do not keep the memory here, the packet will be simply dropped. Only one of the many contending packets will be going to the outgoing port. Okay. And of course, then I told we can probably improve this situation, try to minimize on this loss. I can provide some kind of buffers or the queues at the input port. So the first idea is that I keep the buffers here. These are known as technically input queued switches. Only important thing here is still my switch is operating at the same rate at which the line input lines and output lines work. Okay. That is I think I have mentioned earlier. If there is a contention, I actually allow one of the contending packets to go to the outgoing port, remaining packets are kept in the buffer. So it is possible the same some packet which has been retained in the buffer cannot go even next time. So what will happen, the packet which is coming in the in that particular slot will be queued up in the back of this particular queue which is held up. This could have been transmitted but cannot be, because somebody is there ahead of it which cannot pass through. And then of course I gave an idea that instead of one queue I can maintain multiple of them for separate outgoing ports, and I will try to resolve as far as possible or the backlogged stuff, but if cannot happen, I will use whatever are the other free outgoing ports for which whatever packets are there, I will schedule them. So I said that instead of one queue you will be maintaining multiple of them, okay, like this for each outgoing port, and we will be picking up from there. So this can take care of head of the line blocking actually, okay. But FIFO discipline inside this queue together is not going to be maintained, that is only thing, but this will work very effectively. Okay. Another option was that I can, if somehow I can actually have a speed up factor inside the switch. Okay. The speed up factor cannot be there if it is a plain crossbar. If I use only a crossbar like this, and there are cross points which are connecting here, which are triggered for every slot depending on whatever combination is required. Sorry, these lines are going to work at the same rate at which you are receiving and the bit is going out. There is no speed up factor, it is 1. If I actually modify this switch, I have not mentioned it explicitly, but that was an assumption that packets do come at the incoming port in the switch, they are buffered. There is some limited buffer. So maybe one packet is buffered for every input. Input queues can still be there, I am not bothered about them, but what happens, I actually have some mechanism. Now it is not a crossbar, it is like With crossbar also I can do space switching, but I can also do time switching also. I can read into memory and write kind of thing also can be done. So, I am not looking at a cross point. Cross point is a circuit switching scenario. I am looking at transferring a byte or a slot. Time switching was possible because I was looking for a octet being transferred from one point to another point. In time or in space, both ways it can be done. So, here if I can actually run a processor, I can actually connect a bus for example, and this bus I can read from this bus using a processor, and if this bus speed is such that I can read all these packets in one single time slot, that is possible. So, this processor can read this packet in one, if there are n packets coming in per slot, 1 by nth of the slot this packet can be read by the processor. It can be analyzed and then it can be pushed onto an outgoing bus if it is a dual bus system, and can be pushed onto the outgoing line. So, there can be output buffers also, but this is not a crossbar, but technically it is still a switch, n by n switch, packet switch. Okay. Or alternatively it can also be a crossbar, but then crossbar has to operate within one single slot period. Technically there will be n small minor slots. So, you will be putting the packets here at some line rate, but when you will read out the packet, that will be done at n times faster rate. Okay. So, each packet will be scheduled in different sub slots correspondingly. Then also I can use a crossbar and I will get all packets here at higher speed, n times higher speed. I can put them in the buffer, outgoing line rate will be same as incoming line rate, that also can be done. So, there are various ways of doing it. So, this bus now can address and can actually push the packets into various outgoing things. If this is working at n times faster rate, it is a n times speed up factor. Speed up factor will be n times. They are always kept as same. They are always kept as same. Okay. I think that is what we have done more or less in the last time. Now, we have to go to the analysis part of it. Okay. So, one of the important thing is that what will be the utilization and what will be the average queue length which will be there in for input queued system and output queued system. Okay. So, let us look at first of all the output queued system. So, there is a speed up factor of n which has been assumed. So, even if all packets are there, they want to go to the same port, it is possible that I can read out all these packets at n times faster speed and write into the outgoing buffer, that is technically possible. So, now look at the outgoing buffer, what happens there. Okay. You have a higher clock rate. It is like what is this buffer? Buffer is technically RAM. Okay. So, what you do is you actually have dual system here in the input side or here. You actually first of all read into this particular RAM, then in the next slot you are writing into this RAM if the packet is coming. Only you do not require any actually memory if you have output buffering. On the input side only you will do this, and this packet will be read at very fast rate. So, this has to be now addressed by the processor and read out at faster rate, n times faster rate. So, I can read out the whole packet in 1 by nth of the fraction, 1 by n of the packet duration, slot duration, I should be able to read it. So, I can read all the packets, I can address one by one each one of them, read it out, analyze and then transfer to the outgoing buffers. If all of them want to go to here, it is fine. The first I will read here, next I will read here, I will do addressing. As I am doing it at n times faster rate, I should be able to read all the memories, all the RAMs. While in the input side, the packet which is coming is being written to second memory. And what will happen is I will simply do once this has been read out, next slot you will be writing here and the readout will be happening from this. All address, everything remains the same. So, just do very fast flip flop. Actual implementation will be something similar. You cannot read and write simultaneously, that is very important. You have to first of all write the whole packet, then only you can do the reading. Reading is done at a faster rate. So, packet is compressed in time technically. There are multiple memories which will be there in each one of these inputs. Okay. So, processor can do that. So, I am taking this particular scenario. Okay.
Writing cannot happen at faster rate. Writing.
No, that depends on the line rate. You do it at faster rate, then you have to increase the speed here also. So, to ensure that all packets are read out and written, even if there is a contention, all n packets can be written into one slot. Because you are doing it n times faster rate, you do not require a crossbar. You can read all packets and then write them at appropriate locations. Crossbar is required when speed of factor is 1. Okay. So, even you can build up a hybrid, you can do a crossbar and a speed of factor of k. So, crossbar size required will be actually smaller. So, some that kind of a scheme also can be built, but I am not actually looking into that as of now. I am worried about the output queued system first. So, how this will be modeled? So, in this queue how the packets are actually coming, that is first question. So, in every time slot, it is not that one packet can come in this queue. I may get no packet, I may get 1, I may get 2 and I may also get n packets in the queue. So, there is a whole batch which arrives every slot, and this batch size itself is variable now. So, if you want to estimate a probability that I packets will be arriving in a time slot, this probability will be what? P is the probability that a packet will be there in a slot. So, on an average n into P, these many packets are coming per slot into the switch. Now, each packet is independent which is arriving. So, with equal probability I can assume it will be going to any one of the outputs. So, with 1 by n probability it will be directed to any one of the output. So, from here this guy will get a packet with probability p divided by n, from here again p divided by n and so on. So, from any output port will get from any input with probability p by n. Sum total of all possible scenarios has to be equal to 1, that probability, that actually will be ascertained here. Yeah, this is a uniform loading.
Previously we talked about n minus 1 ports, p by n minus 1 individual probability outside, previously packets.
Yeah, right. Now I am not bothered, this is a transit switch kind of thing, but you are right, I should not be sending a packet back to myself. Okay, that usually is true. That was I think some other case where we considered this. I am actually keeping it n also does not matter, because n I will ultimately will be taking n tending to infinity. So, for that kind of hypothetical switch we will try to compare the throughput performance.
Cross n and speed of factor is same in n.
Speed of factor has to be n if the output queuing has to be implemented, otherwise output queuing cannot be implemented.
Why?
It will become a hybrid system if speed of factor is k. There is a probability, finite probability that all packets which are coming are directed to one port, and this all packets cannot be pushed to one port unless I am reading at n times faster speed. So, in one single slot I am going to read n packets, that is why n times more speed is required inside the switch, then only output queuing can be implemented. If you are ensuring there is a mechanism or discipline or whatever it is by which you say there will never be more than k number of packets being directed to one single outgoing port, where k is less than n. If this can be ensured somehow, or your traffic has that thing, then only k times speed of factor is good enough to implement a output queuing system. But then of course you require a crossbar because you are doing parallel transmission. Here only one packet is being read and one is being transmitted out in one subslot, and there are n subslots. So all packets are read out and transmitted to all outgoing ports. But there you will be requiring crossbar because there are k. There may be actually n packets coming, only k can be read in that subslots, k subslots are there. What happens to the remaining packets? There has to be some kind of a crossbar mechanism which is required, parallel paths. Okay. So this probability will be, this is NCI, combinatorial n factorial divided by I factorial divided by n minus I factorial. This actually comes from basic elementary probability theory. P by n is a packet arrival, so there are I packets which are arriving. I am saying these I packets, so this has to be I. The packets are not directed to me, that probability is this n minus I, and I call it AI. From here I can find out a probability generating function AZ. I will be directly using certain results without proving them because those you can then you have to refer to the probability theory for the proofs. Okay. I think each one of you understand what is a probability generating function for a discrete probability. These are discrete probability. I can only take discrete values 0, 1, 2, 3 to n. The probability generating function is usually defined as z raised to power I, probability of I goes from whatever is the valid values, that will be your P of z. Okay, that is a PGF. It is like Z transform, honestly speaking. It is like Z transform. So, but this is a property because once I know Z transform, and when two variables add, I can actually do the find out the Z transform of the combined stuff. Okay, so I will use those things directly. So AZ in this case will be given by, you can actually plot, put whatever is this AI, this is what will be AZ. So you can actually solve for this. So this will be Z P by, I have just included Z inside, and this is a complete binomial going from I is equal to 0 to n because there are no other possibilities. So I can write this. Okay, this is what will be the Z transform. And of course, if n goes to infinity, in that case AI will be what? A Poisson statistics. This I think was also a standard result. This is what it will converge to. I remember this probability NCI P raised power, you must have done in terms of P and Q, I think. So when you do this, your n into P conversion goes to lambda kind of thing, must have done that way. Okay, and this then converge on to lambda raised power I e raised power lambda divided by I factorial. So Poisson statistics. So I am actually technically use same thing. Since it was P by n, so capital N into P by n, in limit will always become equal to P. So, for the Poisson when n goes to infinity, your A of z will be e raised power minus p 1 minus z. This also you can get from here. Take this Az, okay. This itself can be converted to 1 minus so this whole thing will become nothing but E in limit. That is what I have written here. Okay. This whole thing will be E. So, this will be the second expression. Now, here actually one important thing which is there, since it is a batch arrival, I am not actually proving, I am just stating all the results straightforward. So, QM will be the number of packets which are queued up for the queue corresponding to output I. Okay, this should be equal to maximum of 0 or whatever was the earlier batch plus whatever were the arrivals in the current time slot for output I, which comes from the probability distribution which I had written earlier, minus 1 which will be successfully transmitted. So, if sometimes it is possible that you have only this sum is 1, 1 minus 1 becomes 0. Okay. So, this value can never be smaller than 0, that is why that maximum operator has been put, maximum of the two. So, this is the batch arrival thing.
The argument inside the max, what is the second argument mean here?
AMI is number of packets arriving for output I in mth slot. So, that probability distribution is given by whatever is there. This is going to have this particular Z transform. Az is nothing but probability generating function for this variable AMI. QM is the queue, number of packets in the queue. Mth is the time slot.
I we are taking as the number of packets arriving.
No, this I is summation. After once you do, it's all gone.
Dummy variable.
It's a dummy variable. No,
That I is gone. Now this I is taking out different.
This I for the output.
I is output.
I is output.
Yes. I is very commonly used. I and J are used for dummy variables for summation. So I think you should be able to, by context, should be able to figure out. So QM is number of packets in output queue I in mth time slot, after mth time slot actually. After mth time, because mth time slot you will be getting the packets. No? This one, this is at the end of m minus first.
Sir, if I am taking qm minus 1 in the summation term, here I am assuming that whatever packets are buffered in up to m minus 1 slot, that can also come in the current m slot. So
what is happening is, you have a queue. At m minus first slot there was some size. This size was q of m minus 1 I. In the mth slot, what will happen? New batch will be coming. So that batch will now fill it up. So this size will be AIM. In this time slot, one packet will also go out in mth time slot. So I just remove this is minus 1. So this is a size which will be there left at the end of the mth time slot. That is what it means. Okay. And of course, you can build up a Markov chain, and if you try, you can build up a balance equation, but I am leaving it, I am not doing that actually. The Markov chain for this particular queue will look like something. For example, you are in 0 state. If there is no packet comes, you come back to the same state. Okay. Probability that packet arrived is 0. Probability that one packet comes, it will also go out in that same time slot. So at the end of it again you will be 0. So A0 plus A1, the same probability is AI which I have done from there. This has no role for us, but anyway I am still describing. I will come here if I have A2, one of them will go out, other one will be queued up. So that will be the queue state. I can have 2, I can have 3 and so on. From 0 I can come here if I have A3, A4 and so on. If I have An, I can go to n minus first state from here. From 1 I can come back, if no packet is there, one packet will go out. If there is one packet, I need 2 packets to come in, because one will be going out. One packet is going out, 2 packets comes in, A2, then only I will come to state 2. Sorry, one packet, sorry, it should be A1 here, not A2. Just a minute, it has to be A2 only. This packet will be going out, 2 will be coming in, so you will be in state 2. You will remain here with A1. Okay.
A1 will go back to state 0, A0 will stay in 1 only. One packet is.
This state means how many packets are queued up.
One.
If there is no packet arriving, which is A0, what will happen? This queued up packet will go out. What is in the next state?
0.
There is no packet now.
0.
0. So 1 to 0 you are coming with A0. If there is only one packet in the buffer, no packet arrives, what will happen? This packet will go out, will be transmitted out. Next state of your buffer will be 0. So it will be coming back here. So this is unending like this, A2, A3. This is a standard Markov chain given in all queuing theory books. So for this kind of system, which this is batch arrival process, I can actually build up a, so this kind of queue, I can now build up what we call, I basically require what is the probability that you are in this state, what is the probability that you are in this state, what is the probability you are in this state under steady state conditions. So you can start with building up balance equations, and sum of all probabilities has to be equal to 1 with that kind of thing. You can even solve this. Okay. So people have done that, and in order to represent all probabilities, I am representing them by a probability generating function. I can generate all probabilities with this, all state probabilities. So QZ for this, I am just taking the result, I am not proving it. This will be 1 minus P, 1 minus Z, whatever was the PGF, probability generating function for AI, the arrival process, you have to take that minus Z. And once you have a probability generating function, I can find out the mean value. So from here you can find out what's the mean queue length or average queue length of the output buffer system. From here you can find that thing out. So how you will do it? No, not latest theorem here. This is the PGF, okay. And what is your this is your I bar or A bar you can call it actually. This is a mean. There is nothing but mean queue length, and for this I know this already, this expression. For here if you can take the derivative of P of Z, this will be I Z I minus 1 P of I goes from 0 to n, 0 to infinity, and if you put Z is equal to 1, what you will get? This. So for finding the mean, you simply take the derivative of probability generating function and put Z is equal to 1. Yeah.
The expectation of
This is expectation. Expectation of I. Summation of all probabilities will be always, yes, 1. So that's why if you put Pz, so P1 is always will be equal to 1. Probability generating function at Z is equal to 1 will be always 1, because then that is nothing but sum of all probabilities. Take the derivative, you can find out first movement, second movement, third movement and so on, and henceforth you can find out any movement around any kind of value, that is possible. So variance also can be estimated with this. So all complete statistics is available here for a discrete system. Now similar thing does exist even for continuous time variable, continuous variable probability density functions. Okay. So we also have something equivalent there also, but I am not bothered, I am bothered about only discrete. So this is a very commonly used technique. So once I have this, I can from here estimate what is Q bar. So I am not solving it, I am directly writing the results, you can try it out.
It comes from standard result of queuing theory?
Yeah. So you have to look into either Klenrock or any other book. Klenrock is one of the famous ones, 3 volumes I think. Leonard Klenrock. There are many books available in the library, you can search. But this is a standard result for batch arrival process. So since I am going to use only the result to analyze, so I am not bothered about the results derivation. So Q bar will be coming out to be from here n minus 1 by n two into 1 minus p. Okay. Again this is a standard result. This result interestingly is nothing but n minus 1 by n. This particular part of the result, what you get for a special kind of queues known as MD1 queues, MD1 infinity queues. This actually means there is a queue, here arrival is Markovian, the departure is deterministic, okay, MD1 queue, and there is only one server and buffer length possible is infinite here. For that the average value turns out to be always p square divided by 2 divided by 1 minus p, okay. So this value, so it is nothing but n minus 1 into what I call the Q thing for MD1. So this is the only variation, multiplying factor which comes because of batch arrival.
What is meaning of D?
D is deterministic. Deterministic service time. It's basically constant service time.
Constant.
Deterministic means constant service time.
One is
One slot is service time for every packet.
one is the queue.
One is one queue.
One. Now what is the infinity?
Infinity is infinite buffer length. If there is a finite buffer length, you cannot restore, you have to drop the packets. So packet loss probability comes into picture there.
So what is Q bar? Q bar.
Q bar is average queue length.
So it is this D bar that will determine how many packets will go to the output of the queue.
What?
This D bar factor.
D bar is what?
The service time, determines the service time.
That's a constant slot period. No? One slot period is deterministic. So every packet is serviced in one slot period. It takes only one slot for a packet to be transmitted out. For that, this is the thing. Where P is the probability that in the slot a packet will be there. Okay. So this is what you will get. So N only comes here. The batch effect is here. Remember. And when N goes to infinity, what will happen? N is so large, this 1 can be neglected, N by N will be cancelled. Is SFS as good as is MD1Q. Okay. So batch effect does not matter. So that is, I think, one important thing. Is a Poisson statistics. Is basically exponentially distributed inter-arrival times.
The same is a Poisson distribution.
If you start counting the number of packets coming in a duration, that's Poisson. But between two packets, what's the gap? That's exponential distributed thing. So exponential distributed inter-arrival time is what is known as Markovian process. Now the question is how much time a packet will be waiting before it goes out. What is the waiting time in this switch? So your switch is working at a speed up factor, okay, already. So only delay in the output queue, that's what will be the delay faced by every packet, and that also can be then estimated. So technically there will be two delays which will be there participating. You do certain packet, you just sit on that packet, you tag it, and then see what is suffered by this packet statistically. Whatever it is suffering is also suffered by other packets. You are picking up any packet randomly and tagging it actually, and then seeing what is happening to this. So to look at all possibilities, and from there you can estimate the average waiting time. Okay. So average waiting time W will be two parts, W1 and W2. So W1 corresponds to, this will correspond to something. Even if you arrive, there is already buffer has lot of packets. You are arriving in mth slot, but whatever are there in the buffer already, they are occupied till this point. You will always be coming only in this place. In the mth slot, these many packets have come. So W1 is nothing but this delay. This much you have to suffer, you have no other option. Now the packet which you have tagged, in this AMI, this packet can be the first packet, it can be second one, it can be this, it can be this. Okay. So I have to find out statistically what's the value. Remember, this delay W1 and this delay which is going to be suffered here, which is W2, are independent of each other. So I can simply add them to find out the average. Okay. So W1 will be nothing but Qm minus 1 I. Okay. Those many slots you have to wait. So that will be your W1. And if I want to find out an average value, I have to just take the bar of it. Once I take the bar of it, m minus 1, m minus 2 does not matter. Statistically, this will be nothing but Qm bar, which will come from there. So what is the W1z? PGF of this will be nothing but Q of z, whatever we have solved earlier. Same PGF will be used here. W2 is slightly tricky part. So W1z is nothing but 1 minus P, 1 minus z, Az minus z. So coming to the next one, this is slightly tricky, because we have to now find out W2. So, W2 will have first thing, whatever is your tagged packet is coming in a batch of I. Again, I is a separate index here. Okay. This is not that number output port number, no. This I is again I am using as a new variable. Okay. So, the tagged packet is coming in batch of I. What is this probability? So, the tagged packet must be coming from one of the ports, and this port cannot send another packet. So, remaining n minus 1 packets must have sent what we call remaining I minus 1 packets to this particular device. So, this actually means you will have n minus 1 C I minus 1 P by n is the possibility, I minus 1 this is a probability with which your packet will be in the batch of I packets. Okay. Where I is the batch size. So, your tagged packet is going to come in batch size of I, that probability is this. Okay. So, you can solve for this is pretty simple. N minus 1 factorial, I minus 1 factorial, n minus I factorial. Okay. This I can write as n by p I have just minus 1 I have taken here. I can now multiply by I and divide by I. Okay. So, I can write I divide by P N C I P by N okay, and this is nothing but I into A I by P. So, what I want is I want to find out that W2 is equal to K, what is the probability. So, for this what I will do is, if W2 has to be K, I need to have at least batch size which is greater than K, it has to be K plus 1 minimum. Okay. So, if for any batch size, if it is greater than K plus 1, it should be placed in any one of these, always in this slot. If batch size is K plus 1, for example, the probability it will be at this location is 1 by whatever was the number in the batch, 1 over I. If it was K by 2, the batch size is this much, but I have to place it here. This packet could have been anywhere, but to be here it is again 1 by I. If I take this much large batch size, again this packet is going to come here, its probability is 1 by I. Your tagged packet can be placed with equal probability anywhere, but at K place, K plus first place it is going to be placed, that probability is 1 by I, and I has to be from K plus 1 onward to till whatever can be the maximum batch size, which is n. So, this actually means this probability has to be nothing but I is equal to K plus 1 to n 1 over I, and probability that the batch size of I will be there. This is what will be the probability. okay, and this is interestingly nothing but this. So, I think we will close here now. So, tomorrow morning what we will do is, I will start from here, I will build up a probability generating function of this. I already have a probability generating function of W1. I use W1 and W2 probability generating functions to find out probability generating function of W. When W1 plus W2 is equal to W, probability generating function of W1, W1z multiplied by W2z has to be equal to Wz. So, once I know Wz, I can find out what is the mean waiting time in the queue, and I know how this whole thing is going to perform. This is how I think we model this particular switch, and then we will look into the input queuing part to figure out what is the best strategy for operating input queue. So, what is the maximum throughput which you can achieve in the input queued switch? There is a limit, you cannot get to 1, that is not possible because of the contentions which happen.
Maybe 1 by I.
See, 1 by I is the probability that you will be placed at k plus first position, and this can only happen when the batch size is k plus 1 minimum. So, even if you take n batch size, what is the probability you will be placed here is again 1 by I. Your packet can be equally likely anywhere. So, I am put 1 by I is that probability that you are at a position k plus 1 in the coming batch, and there is a probability that you will get a batch of IA, batch of I. Sum of all possible things, get the average value. That is the probability that you will be having W2 is equal to k.